Right, so you all know the drill by now. How's everyone doing? Woo! All right. Okay, so welcome back to the last talk of the afternoon. It's a great pleasure first just to introduce the general subject, especially since this one is very dear to my heart. Particle theory, we have the privilege of being situated sort of in the vast landscape of quantum field theory, and that means a lot of really interesting opportunities. Of course, new developments in quantum field theory often drive new progress in particle theory, but also the very sharp, pressing, and data-driven problems of particle theory help to really give rise to new ideas in field theory as well. And so it was, in mind of that interplay that we decided to create a somewhat open-ended subject for the last week of lectures, which is the idea of the pursuit of new paradigms. And there was absolutely no one better we could think of to give this talk or this series of lectures than Mathew McCullough. Mathew is permanent staff at CERN, which is, I think, one of the best particle theory jobs in the world. And I could spend lots of time here saying nice things about Mathew, but I'll stick to just one thing, which is that whenever I'm reading a physics paper when I'm absolutely supposed to be doing something else, my wife knows that it must be one of Mathew's papers because he always has something amazing to say. So with that, I'll turn it over to Mathew.
Thanks very much, Nathaniel. So first I want to say that I feel tremendously privileged to be lecturing at TASI. This is, I'm sure you all appreciate that this is a very formative moment in your careers. When I moved to the US as a postdoc, I was really amazed at the network of research network of young theorists that already existed within the US. Of people who had worked together or who had discussed physics together at length. And this was all due to TASI, and I was actually, I have to say, very, very jealous of it. So I feel really, it's a completely unique program, and it's a tremendous honor to have the opportunity to talk, to give some lectures here. Some details before I get into the topic. There are lecture notes online. I'm not going to post handwritten lecture notes because my handwritten lecture notes have lots of prompts for me, and my handwriting is horrific as well. Well, you're going to find that out. So please consult the PDF that's already online. It's not the exact same PDF that will end up ultimately on the archive, but it's close enough. Also, I'm relatively chatty. I think this is an Irish thing. So there's lots of blah, blah, blah in there. But I hope you find it sort of amusing. I've tried to keep it a lighthearted style. I have some blah, blah, blah right at the start about what a paradigm is, at least my interpretation of that. I'm not going to take the time, because it's verging on philosophy. I'm not going to take the time to go through that in these lectures, but please, if you're interested, try and have a look at that right at the start of the PDF. I'm going to try and, as much as possible, be economical with my time. So not everything, not even every topic that's in the PDF is going to be contained in the lectures. But I put some other stuff in there because it might be interesting to you. I'm also, within the lectures, not going to tell you necessarily the best references to go to, but within the various chapters in the PDF, I try to provide that. I should say, though, you already know this, if you're interested in a specific topic and it has been lectured on at TASI, then that's most likely the best place to look. So for any of these topics, please consult previous TASI lectures. Okay, so I'm going to start off by asking broader questions about effective field theory, with not only within particle physics, but as a more general approach to solving physics problems. But before I do that, I want to ask you guys if you can tell me, there's been many, of any paradigm shifts that have happened in theoretical physics. Anything that comes to mind where the paradigm changed. Because that's what we need to do, right? We need to find the right new paradigm. Supersymmetry certainly shifted the theoretical paradigm, but I really mean in terms of our understanding of observed experimental nature. So supersymmetry was a paradigm shift in theoretical physics, yes? Wow, yes, okay, that's amazing, yes. Paradigm shifts. One paradigm shift was our understanding of renormalization group and how that fits within the framework of EFT. Before that paradigm shift, we had a very incomplete understanding of many phenomena in nature. Any others? the discovery of the Higgs boson was a paradigm shift, but that sort of, in some sense, confirmed a previous paradigm shift, which in theoretical physics, which was the discovery of the Higgs mechanism, and so on. But I'm talking, you know, really paradigms, broad conceptual ideas that really revolutionized our understanding of physics. Yes? Gauge symmetries, yes, fantastic. One example would be, pardon? Asymptotic freedom, yeah. I'm thinking bigger, guys. Yes. Sorry, yes. The Cork model, yes, but that fits within a framework. Yes?
How about the GR-QM revolution?
Okay, now we're getting places. So one would be a Newtonian gravity to GR. Okay, I'm talking paradigm shifts, really the entire framework, how we view the world changes. Sorry, this was QFT, the understanding of QFT. So the understanding of QFT came about as essentially the marriage of QM plus sort of particle dynamics, let's say. Exactly. Okay, any more? Electromagnetism, yes. That was certainly a paradigm shift. I guess that would be the discovery of gauge symmetry in some in its nascent sense.
Electromagnetic waves, light being an electromagnetic wave.
Yep. Any more? Wow, that's the biggest possible. Yes. Yeah, no, absolutely. That's yeah. That's an excellent example. Yeah. Okay, you've sort of gone to the top.
Can you repeat that?
Sorry. Yeah. The suggestion was using equations to explain physical phenomena. I'm interpreting your yes. Spontaneous symmetry breaking, yes, was certainly a paradigm shift. So a lot of these can be viewed as understanding new effective field theories in some sense or another. Going from one effective field theory to another. Another example that you probably don't really think of so much, but if you think about thermodynamics and statistical mechanics, is this something you guys know about? Statistical mechanics? Yeah, stat mech. To statistical field theory is another where we got a greatly enhanced understanding of phenomena in condensed matter in the world around us. And many of these are really a step from one description, one effective theory, to a broader understanding of an effective field theory or an entirely new effective field theory. You know, this is one effective field theory that breaks down at certain energy scales, length scales, and we went to a different effective field theory, which is, you could say, the traditional description is that we have a gauge symmetry, gauge diffeomorphisms, essentially. Here we went to an effective field theory that worked pretty well for non-relativistic particles and their interaction with light, for instance. But then we needed to go to a new effective field theory if we wanted to extend the scope of to essentially relativistic dynamics. Statistical mechanics and statistical field theory is sort of nice because it really shows, in my view, the emergence of universality. So universality is the idea that many different microscopic systems might have physics that's at long distance scales that's actually captured by the same effective field theory. And this, why I like this is because you start really with stat mech, you really start thinking, you know, you're thinking about lots of different, say, particles or atoms or something like this and what their broad statistical properties are. And then you go towards statistical field theory, where you find statistical field theories like the Landau model and things like this, which describe a broad range of phenomena. So I do this with much more florid language in the lecture notes and try to make the argument that, to all intents and purposes, because I had to try and interpret this, I had the hardest job of trying to interpret what is I'm actually meant to talk about here in terms of new paradigms, that really discoveries of new paradigms, for the most part, not all examples, I think can really be interpreted relatively successfully as the discovery of a new effective description of nature which has broader validity, which is valid over, say, smaller distance scales or higher energies, the two being related. One place where I can't really interpret it that way is the discovery of quantum mechanics. So if anyone has any thoughts on that, what the nature of the discovery of quantum mechanics was in terms of paradigms, then please tell me. Yes?
I think the thing that made that a paradigm shift was because it threw out a sizable amount of what came before.
Yeah, so it was definitely a paradigm shift, but I can't really put it in my box of going from one effective field theory or effective description of nature to another one. It seems to be somehow outside of that. But please. Pardon? About the nature of phase transition. So the comment here was that Ehrenfest's theorem was a paradigm shift for sure, because it was very universal, and can be understood very nicely within statistical field theory. Yeah. Okay, so now I want to move on to ever so slightly more concrete things. So what is the idea of effective field theory, really? I'm going to go across two boards. By the way, I much prefer interaction, so please continue just to shout out if you have any comments, complaints. If you have any comments or complaints about my writing, if I'm not speaking loud enough, if my accent has confused you, because I say some... No, it's a real problem. The tau lepton is a killer for me when I have to try to have conversations about particle physics. So if you haven't understood a word that I've said, please just shout up. I won't be offended. Okay, so what are the ideas of effective field theory? So I want to use electrostatics to try and give a sense of at least my view of what effective field theory is, and then we can go on to think about quantum field theories and so on. So suppose I have some object of size this, and it's made up of, it has within it some arrangement of charges. Now the size of this object I'm going to call R0. It's characteristic, right? This is not a sphere, this is something else, but it's the characteristic size of that object. And suppose I'm a distance r, where r is much, much larger than R0 from this object. I want to calculate what the electrostatic potential is way out here, where R0 over R is a small number. The approach of an ineffective theorist as compared to an effective theorist, an ineffective theorist would say, well, okay, anytime I have one of these objects, what I will do is I will calculate the positions, or determine experimentally, whatever, the positions of all of those charges or the distributions of the charges within that object, and then I'll just add them all up and use Coulomb's law, and I'll write down the potential. Now that works, but number one, it's a very laborious process. And number two, it's sort of missing the wood for the trees in terms of understanding the form of the electrostatic potential of that object. The effective theorist would say, okay, I'm going to look at the symmetries of this object. I want to know the broad properties of this object, and particularly relating to the charge distribution. And from those symmetries, I'll be able to write down for you very quickly, with very little effort, the most important terms in this electrostatic potential. Okay? For me, that's essentially the core of the approach. So you will have done this, I'm sure, as undergraduates, but I just want to go through it quite quickly. So one example of great effective field theory style approaches, I will get to field theory, this isn't really field theory, is the dipole. So I'm sure you've all studied the electrostatic dipole as undergraduates. So I'm going to work in spherical polar coordinates. This is the z direction here. And this distance here, let's call it d0, d. That's the size of the dipole, the separation of a positive and negative charge. Now, the ineffective theorist would say, well, okay, I can immediately write down the electrostatic potential. It's this thing here. It's 1 over root of, in spherical, cylindrical coordinates, r squared plus z plus d over 2 squared. You're not allowed to complain that you can't read this, because you should be able to just write this down yourselves.
I was actually just about to complain.
Yes. If you're here, you should just be able to write it down yourselves. R squared plus z minus d over 2 squared. Okay, this is what the ineffective theorist would say. This is, and they're correct. Okay, but as I said, it's missing the wood for the trees, because the effective theorist would say space here has an SO3 symmetry, and I only see one parameter that breaks the SO3 symmetry, and that's the vector between these two charges. So there's only one parameter that's breaking the SO3 symmetry. So, and here, if I'm a long distance from this dipole, then that parameter is small as a ratio to this distance, whatever it is. And so I can say, well, right from the get-go, that the potential, in terms of, I'm going to call the coordinates x in Cartesian, is approximately, to a good approximation, d dot x, where d is the parameter that's breaking rotational invariance, divided by the distance cubed, because after all, this is, by the way, I'm setting all electromagnetic constants to 1, because we're just looking at scalings here. So I know Caitlin approximated pi by 3 and 10 and so on. I'm doing much worse than that. But we just want to know the scalings. But in any case, it's going to go like 1 over distance. So if I have d dot x in the numerator, then there's got to be x cubed in the denominator. And so in cylindrical polar coordinates, this will be dz over r squared plus z squared to the 3/2, which is what you would have found if you expanded this to leading order in d, plus other terms that I'm not so worried about because I'm a long distance from this dipole. Okay, so here you would say that what you did here sort of sounds clever, but I could have also just done this, right, in probably first year of undergrad. I don't know, maybe second year of undergrad, depending on what your majors are and so on. So what have I really gained? Well, what you gain is that when you go to much more complicated scenarios, effective field theory really starts to win for you. So I give an example in the notes. I'm not going to go through it very much. But I give an example in the notes based on Buckminster-Fullerene. Does anyone know what Buckminster-Fullerene is? Has anyone come across this? Caitlin does. Yeah.
Is it like the buckyball, like the 60 carbon seals?
Yes, brilliant. So sorry, who's this again?
What, my name?
Yeah.
Ian.
So Ian said, isn't this like a buckyball? Yes, with 60 carbon atoms. So indeed, Buckminster-Fullerene is an arrangement, it's a molecule of 60 carbon atoms, which has exactly the same symmetries as a soccer ball, which is very pertinent because it's the Euro Championship at the moment. And so you can, if you want to study the symmetries of buckyballs, you just need to turn on your television. Now, a buckyball is a complicated thing. If you look at it, I've given a picture. It's also a very beautiful thing. It's a very complicated thing. But if you wanted to calculate the electrostatic potential around a buckyball, and you were going to solve for all of the atomic orbitals in that molecule, and then those wave functions, and then go a long way from it and add them all up, you'd be doing a lot of work, right? Okay, you would be doing way more work than you ought to do if you're a long way from the buckyball. The buckyball is like a sphere, and if it has some size, let's typical size, which is R0, and you were to go through that process, then you would waste a lot of time. But using symmetries, you can recognize that the buckyball has a special symmetry. It's called icosahedral symmetry. And this is a subgroup of rotations of SO3 symmetry. And then you could look at all possible representations of the rotation group that preserve that symmetry. And you will find that the smallest representation that does so is a representation that has 6 indices. So it's a representation it's an irreducible representation of SO3, which has 6 symmetries. And so then at leading order, the lowest term in the potential that you would get for the electrostatic potential that you would get for the buckyball. So I should move this slightly down, but I won't go too far down. is of the following form, of the typical scale of 0 to the n, where n is the number of indices in this representation. Call R this representation, a1 to an. Then all of the vectors, I should call them x possibly, but if you just think of R as being as being a vector, or a1 all the way to R an, right number of R's to have the dimensions of an electrostatic potential, and you've got 1 plus n. And for the buckyball, it turns out that you can just write down what this is explicitly, and the potential has the following form. It looks like R0 to the 6 over R to the 13, a very, very steep potential, times x squared minus y squared minus z squared minus x squared. So there's a permutation symmetry. And so this is much easier. Then there'll be higher order terms that are suppressed by higher powers of R0 over R. Sorry, that's a 13 in there. If you can't read it, that's 13. And this is much easier than calculating all of those electron wave functions and so on. So what are we doing here? What's the process? Well, the process is really to identify what symmetries there are left. So you start off with rotational symmetry, SO3 symmetry. You're identifying what symmetries are left in the presence of such an object. You're parameterizing the breaking of those symmetries by some parameter, which is in a representation of that symmetry. We usually call that parameters like this spurions. Who's heard of spurions before? Oh, wow, excellent. Okay, this is going to make the lectures go a bit faster. So you identify the spurion for the dipole. The spurion for SO3 breaking was just this vector. And then you just follow dimensional analysis and everything falls out. For the buckyball, the spurion was more complicated. It was some 6-dimensional irrep, but nonetheless, you can find out what it is, and you can find out what the values are of this irrep. It's traceless. The irreps they're irreducible, so you can't make them smaller. So if you take the trace over any of these irreps, by the way, you just get 0. And then you write down all of the terms that are allowed, and you get this as the leading term. So now I want to go on to the sort of general concepts and general approach of effective field theory. If they're incomplete, then just shout out, and we can add concepts. The first is scale separation. In order for your effective field theory approach to work well, you have to have some small parameter that you can expand in, such that you know you're capturing leading effects when you work to lowest order in that expansion parameter. In these cases, it was in the case of the buckyball, it was R0 over R, which was a small number. And the same you'll see to be true in quantum field theory. The second important concept is symmetry. In the sense that symmetry is your guiding principle. Symmetries radically constrain the forms of effective field theories. And so when attacking a problem where you need to use effective field theory, one of the smartest things you can do is first try and identify all of the symmetries in the problem that you're trying to understand. And then they will usually lead you to the answer. And they also tend to organize an effective field theory. You know, in this sense here, we were using the symmetries to organize the spurions. The spurions are in irreps of spatial rotations. So we use that as our organizing principle. The next is dimensional analysis. It's incredibly powerful. Things should scale in certain ways, right? I used it twice here. I know that this is an electric static potential, and so it should be proportional to 1 over distance in the end of the day. And so I already know how many powers of this ratio, R0 over R, there have to be in front. The next thing is the cutoff. Effective field theories, by nature and by design, are not valid over all distance scales. If I were to use this effective field theory, or this isn't a field theory, this effective theory to describe the dipole at distances smaller than d, I get something that's just complete garbage. And so by design, an effective field theory has a regime of validity, and part of that regime of validity is the very end of that regime where you know it breaks down, and that's called the cutoff. So here the cutoff is around d. Don't use this effective field theory for distances approaching d. You see, d is sort of the shortest distance scale you can go to. In quantum field theory, that would correspond then to the highest energies you can get to. And the cutoff should not be misunderstood. It's a part of your definition of your effective field theory. It's telling you when it breaks down. Now, if you're working with an effective field theory where you don't know what the microscopic physics is, for instance, in this case here, I might have told you the first few leading terms in the potential, but I might not have actually told you what the actual distance scale is. Then you have to remember the cutoff. You have to think about it, because you may not know what the cutoff is, but you need to be cognizant of the fact that it exists. And so you may, when you're extracting physics from your effective field theory, it may break down. Now, this also applies in quantum field theory, and it's not the same thing as the cutoff you use in a loop integral. Okay, the cutoff that you use in a loop integral is scheme dependent, right? You know, dimensional regularization, essentially that cutoff is related to epsilon. Pauli Villars, there's an energy scale associated with the cutoff. That's a separate thing. Sometimes when we want to make estimates about the magnitude of effects in quantum field theory that come from the UV physics, we might use the loop integral and look at how the result from that loop integral depends on the cutoff to give us a sense. But that's just a very sloppy, in my view, abuse of the cutoff. But the cutoff. But the reason I say this is you might confuse yourself into thinking that when you're just doing loop integrals and you're just working your way through Pestel and Schroeder or whatever, that the cutoff is just a purely scheme-independent thing. You don't need to worry about it. The cutoff in an effective field theory is very much part of that effective field theory, and it's very much a physical thing, even if you don't know what it is. Sometimes you will know what it is because you will know exactly the mass scale of the states that you've integrated out and you're ignoring, but in the low energy description, or you're not including explicitly in the low energy description, but sometimes you might not know it. Another important concept is sometimes called the totalitarian principle. Otherwise known as everything not forbidden is compulsory. This is, I think, someone can correct me. I think this is first attributed to Murray Gell-Mann, but I'm not sure. Is that correct? Yes? And what this means is that if there are terms that in your effective field theory that are not forbidden by any symmetries, then they will typically be generated, even if it's not at leading order, at the quantum level, they will typically be generated. They don't necessarily have to be big. You know, they could be accidentally small in your effective field theory, but they're never going to be identically zero. There will always be something that shows up at some high loop order or whatever that generates them. If they are identically zero, you should start asking yourself, are there symmetries here that I'm not aware of? Which does occasionally happen. And the last one, for these purposes is accidental symmetry. Can anyone tell me, there's no wrong answer to this question, by the way. Can anyone tell me what accidental symmetry is? If not, that's totally fine. It's not a problem. Nope. OK, well, I'm going to give an example. So accidental symmetries are symmetries that sort of emerge, you might call them emergent symmetries, in effective field theories as you go to lower and lower energies or larger and larger distance scales. So I'll give an example. Consider that dipole that we thought about before, but consider it in the case where both charges are positive, so it's no longer a dipole. So you have plus here and plus here, still separated by d. So now, and we're a long way away from it again. So we want to describe the electrostatic potential as an expansion in d. But now you have both charges, so you do get the usual Coulomb term. So you get something v of the coordinates. I'm going to work again in cylindricals. It goes like 2 over the distance, r squared plus z squared to the half, multiplying 1. And then the leading next term enters at d squared. And you've got 2z squared minus r squared over the distance, r squared plus z squared squared, plus higher order terms. Now, as we go further and further from the dipole, this term becomes smaller and smaller compared to this term. If you stare at this term, you'll see that it doesn't respect rotations. It doesn't respect SO3 symmetry. But this term respects SO3 symmetry, right? This is just the distance from this object. And so what's happening is you're going further and further from this object is you're seeing more and more SO3 symmetry and less SO3 symmetry breaking. And this is basically the notion of accidental symmetries. As you go to longer and longer distance scales, the theory can become more and more symmetric because in a quantum field theory, operators that break symmetries might be, we would say, irrelevant. They become less and less relevant as you go to longer and longer distance scales. Can anyone give me an example of an accidental symmetry that might exist? It probably doesn't, but might exist or does exist in the standard model if you believe that standard model to be the thing on the front of the T-shirt that you buy at CERN. Any ideas? Yes? B minus L, but it's yeah, B minus L, actually. Yep.
How do we know that B minus L is an accidental symmetry and not just a real symmetry? There's no term in standard model that breaks it.
Exactly. So that's a good point. So the point from Jonah was that how do we know B minus L is an accidental symmetry and not just an exact symmetry? And the answer is we don't. But if the UV theory, the UV completion of the standard model does break B minus L, then as we go to lower and lower distance, longer and longer distance scales, we expect to see it emerge in any case as an accidental symmetry because you simply can't write down an operator that's relevant in the standard model that breaks B minus L. Okay, this is excellent. Okay, and one final thing I want to mention, which is much more wishy-washy, and I'm already being very wishy-washy, is clues. Now, this is very important if you're really thinking about structural questions. Often we're in a scenario where we're using effective field theory even though we know the full theory. But in the full theory, calculations might be intractable or difficult. Yet in the effective theory, you have some small expansion parameter. Maybe it's a small distance over a big distance, or maybe it's a velocity, a small velocity relative to the speed of light. And we might use the effective field theory because that just makes calculations much, much easier. And so you can do those calculations. You see, an example of this would be the effective field theory approach to calculating the gravitational wave signatures of binaries and things like this. However, when we're thinking structurally, there are scenarios that come up where we don't even know what the UV physics is. And then we have to stare very hard at our effective field theory and look for clues. Those clues could come in the form of the symmetries that you see. Like Jonah pointed out here, maybe the standard model is telling us that there's something fundamental to B minus L. You know, that's a perfectly valid question to ask. There might be clues built into the effective field theory that you're working with that give you hints about what's going on at small distance scales. One example would be, you know, if you're doing a general expansion in some spurion, some small parameter, and you find out that that expansion is converging very, very quickly. The terms, each of these, the terms in that expansion have coefficients that are becoming rapidly smaller. That might tell you that For instance, the UV completion is weakly coupled or something like this. And these clues are tremendously useful, and we shouldn't forget the role that they play, because certainly BSM model builders like myself or Nathaniel, we spend a lot of time looking at clues and trying to make guesses about the UV theory. But this is actually an age-old effort. This is really how the standard model was constructed, right? QCD with quarks, SU2 cross U1, and the leptons and quarks as well. All of that stuff did not just fall out of the sky, right? It was constructed by looking at the clues in the effective theory that one was studying. For the case of the electroweak interactions, that was the Fermi interaction and some other clues. For the case of QCD, that was looking at the patterns in the IR effective field theory, the patterns of baryons and mesons, their masses and their interactions. And people stared at those clues and actually wrote down the correct UV completion before experiment had got there, which is really a phenomenal achievement, but it's also the sort of standard that we should hold ourselves to. So clues are a big part of thinking about effective field theories. Are there any questions about any of this? Because I'm about to move on. Or comments? Or anything you think I should add to this list? Yes?
I might add matching.
Matching is certainly, yeah, absolutely, good one, matching. So matching is what you do when you're working within the UV theory. And as I said, you might know the UV theory, but want to work with an effective theory because that might make certain calculations tractable. And then what you do is you work within your UV theory and you match to see what the coefficients of the various terms, see here, what the coefficients, for instance, between here and here in the next term and so on are. You can calculate them from within the UV theory to determine not only the structural aspects of your effective field theory, but actually the quantitative coefficients. Any other things anyone would like to add? That was a great addition. No? Okay, well, let's move on then. So how does effective field theory work? I'm going to just use this side of the board because then I can start higher up. In quantum field theory, because what I've been doing is not really effective field theory, right? I've been talking about electrostatics. Yeah, there's been no fields. Well, I guess the electrostatic field, electromagnetic field, but not in the way we're about to treat it for the rest of these lectures. And so all of these concepts essentially map across in many cases. However, something we come across a lot of in quantum field theory is that spatial symmetries become also accompanied within quantum field theories by internal symmetries. That there might be some internal symmetries that are like B minus L would be one, right? This is not a space-time symmetry. But many concepts map across. So I'm going to use as an example, because it's going to relate quite nicely to the electrostatics example. Imagine we had an effective field theory where we had a vector of scalar fields, 3 of them, phi 1, phi 2, phi 3. And imagine that in our effective field theory, there's an exact SO3 symmetry. Then to start working with our effective field theory and calculating things like scattering amplitudes, for instance, we would start off with our Lagrangian, and we would write down all of the normal SO3 invariant terms. So we'd have something like -1/2 phi box phi, that's the kinetic term. I'm dotting together indices here implicitly. I'm not going to write them because I can't decide whether I want to put the dot here or here, so I'm just not going to do it. 1/2, a mass for this scalar. Pardon?
It should go on the left of the box.
Left of the box. Okay.
Because box 5 is a vector.
Okay. I'm happy. A quartic interaction is allowed by the symmetries. Let's put 12 here. Phi squared squared. But also higher dimensional interactions. I call it C6 over m squared, but then you can have terms like this one, but with more derivatives. Phi box squared phi. Higher order interactions with derivatives. I'll call it lambda 6. C6 is just some number. that if you knew the UV completion, you would be able to determine from matching. Phi squared box, phi squared plus kappa 6 phi squared cubed. And then there could be other terms. And so we can interpret here m as what we would call the cutoff in this theory. I call it m and not lambda because the cutoff is really, if you're thinking about something like scattering amplitudes, it's really the sort of energy scale at which you would expect new states to show up. So it would be, there would be poles, you would see poles, or a branch cut or something like that in a scattering amplitude. I'm not going to talk about redundancy here. Who knows about redundant operators in effective theories? Yes, Caitlin? Yes, oh, okay. Oh, sorry, I thought that was so quick that I thought you had your hand up before I asked, which would violate causality, of course. So who knows about redundancies? Who else? Yes, okay, so quite a few people. So redundancies are the fact that this actually is a redundant description of the physics. You can actually remove, an operator here by using the equations of motion, but I'm not going to go into that. It's important, but I'm not going to go into that. What is more important here is that this theory, it will break down. So the cutoff is a real thing. You should worry about it. If I were scattering, for example, 2 into 4, this is just one example. You can pick many of them. 2 scalars into 4 scalars. And here, I would have the propagator, which would look like 1 over p squared minus m squared. Sorry, that's too small. Let me do it down here. 1 over p squared minus m squared, multiplying 1 plus c6 over m squared, p squared minus m squared. And you see this term here is growing relative to the leading term with p squared over m squared. So when p squared gets up to m squared, this is an order 1 correction, and your effective description is starting to break down. Okay. Yes. Oh, sorry. Yes, thank you. And in here. Little m, little m. Okay. And we can even examine this question of emergent or accidental symmetries, because imagine I lied to you. Impossible, but imagine it could happen. Imagine there was no SO3 symmetry. That in fact, I was talking about a theory that didn't have SO3 symmetry. It only had a symmetry known as A5. Now, A5 is what particle physicists call the icosahedral group if they're talking to condensed matter theorists. And then A5, I would have, if I had just the A5 symmetry, not the full SO3 symmetry, I could have had interactions, I'll call it KR, that look like this, m squared, where again, I would have the exact same form of irrep that I talked about over here for the icosahedral group, but now it's for an internal symmetry. It's not for spatial rotation symmetry. This is for internal symmetry acting on these scalars. And then again, the same story, A1 to A6, phi A1 to phi A6. And again, you get the same form. So you would get something like kappa, I call it kappa R, over m squared, phi 1 squared minus phi 2 squared, phi 2 squared minus phi 3 squared, phi 3 squared minus phi 1 squared. Okay, so why was I able to lie to you so easily? The reason is because you see that this the explicit symmetry breaking from SO3 down to A5 only arises as a higher dimension operator, as a dimension 6 operator here. Which means if I go down to low energy, say I'm scattering just 2 to 2 scattering, I don't see the existence of this operator. Say I only have enough energy in my collider to produce 2 of these particles and scatter them off each other, and I'm just above threshold. At that low energy scale, I can't access this interaction. I don't know it exists. And so in that case, you see, again, in a similar way to the electrostatics, that you have an emergent symmetry that at low energies, this theory looks SO3 symmetric, even though at high energies, you find out that that is not the case. Okay, and there's, in this context, there's one last thing I want to talk about, and then we will go on to paradigms. And this last thing is known as H-bar counting. So we'll take a poll here. Who likes to set H-bar to 1? Notice my hand is not up. Okay, so yes, setting H-bar to 1 can be helpful. In, I guess in principle you don't lose any information when you do that, but you do lose information if you're not being super duper careful in the way you're looking at things. So I find it, I'm lazy. I like the math. Sorry, I'm in US. I like the math to tell me directly, immediately, as immediately as possible, what's going on. And so I don't like to set H-bar to 1. If you don't set H-bar to 1, then you can actually essentially count quantities in units of H-bar. And this can be tremendously useful. So if you do that, you've got, if you're working in a convention where you've 1 over H-bar in your action, then the dimensions of a field would be the same as the dimensions of H-bar to the half. You can see this from the kinetic terms. If I have 1 over H-bar and the whole action has to be dimensionless because it's going, after all, into the argument of an exponential, then if I have two fields, then they must, this is a space-time derivative. I've got the integral over space-time, so that's all space-time. Then the fields must have dimensions of H-bar to the half. But so too, if I have interactions, then I have more fields. So too, the couplings, like gauge couplings, Yukawas, must have dimensions of H-bar to the half, same as a field. Now it's H-bar to the minus a half to counteract the field. Chordic couplings would have dimensions of H-bar to the minus 1, and so on and so forth. This kappa r in here, see I've got 6 fields, so that has dimensions of kappa r. That has dimensions of H-bar to the minus 2, and so on. So that's very sloppy. Now this, you might say, I don't care. I can still just do my loop calculations and get on with my life. But the point is that this can be tremendously powerful. So I want to give you one example. This interaction has this parameter, kappa r. So suppose I wanted to determine at what order this whole interaction will enter into the 2-point function of the scalar field. So you would have something like, you've got 2 phi's here, you've got 2 phi's here. Those are the things that are captured by the 2-point function. How many loops do you have to have before that happens? Computer says no. So you can use H-bar counting to determine this, because kappa r has come along with this tensor here. This tensor is traceless. So if I wanted to have one insertion of this into something that is SO3 symmetric, it wouldn't work, because the only way to do that in an SO3 symmetric way would be to trace over some pairs of those 6 indices. So that's not going to work. So that means I need to have at least 2 R's, 2 of these tensors, because then I can absorb some indices. Maybe some of the indices will also be picked up by 2 of these phi's, but there's only 2, so I can't pick them all up. So I'd have to have at least 2 of these R6s. If I've got 2 of these, then I've got 2 of these kappa R's. But kappa R has dimension of H-bar to the minus 2. So if I have 2 of them, that's dimension of H-bar to the minus 4. But overall, the whole thing is going to have the same dimensions as this here, and the phi's are carrying my H-bars. So from that alone, I know that I have to have 4 loops. So this thing is only going to show up in the 2-point function at 4 loops. Now, of course, you could draw Feynman diagrams and play around with those and get to the same result. That's not the point, but you have to do a lot less work often for these sorts of questions if you think about H-bar counting. Okay, Great. So now we're going to move on to talking about new paradigms. So now we're going to go on to particle physics. Why do we need new paradigms in particle physics? Any suggestions? What about gravity? Okay, why new paradigms? Yep. So that's a great example. So GR, as you go to very high energies, if you're scattering gravitons or scattering things that couple to gravitons, which can then produce gravitons, that coupling will become strong, and you won't be able to calculate anymore within your effective field theory. And so you need to replace that by something in order to be able to calculate what goes on at high energies. Great example. Any more?
To explain the particle nature of dark matter.
Yeah, like that's a good example. So we need to know what dark matter is. And so that will require a new paradigm, and I would argue a new effective theory. It's possible that the effective theory we discover dark matter, and then we study its interactions and find out that it's described by a UV complete theory, but that's probably unlikely. Any more? Neutrino masses, yes, for sure. We need a new paradigm. We may have already discovered these paradigms, by the way. They may already exist in the literature, but for sure, whatever if we had a perfect collider or a perfect experimental apparatus, and we could go to arbitrarily high energies and fully explore these things, there would be some theory, effective theory, that describes neutrino masses. Any more? Yep. Yep. Yes, naturalness, fine-tuning. In some sense, this is a paradigm on a paradigm, because we know the standard model breaks down. The standard model is an effective field theory. Does anyone know why? There's two reasons. One of them's on the board, which is that the gravitational part breaks down as you go to high energies. So whatever replaces gravity is also going to affect the standard model. Any other reasons? Yep. Yes, excellent. So what was your name, sorry? Sean brought up the Landau pole. So hypercharge. So say, is it flamingos that bury their head in the sand? Yes? Say, ostriches, sorry, yes, sorry. Say you're an ostrich and you're like, okay, I'm just not going to talk about gravity. I refuse to, you can say to me as many times as you want that gravitational interactions become strongly coupled at high energies. I'm not going to talk to you. I'm just going to work with the standard model. I'm perfectly happy, I'm not worried. Because even if you ignore that problem, which is a problem, hypercharge itself becomes strongly coupled at extremely high energies. And so even if you were to treat the standard model as a 4D Minkowski effective field theory, or quantum field theory, it breaks down and needs to be replaced by something. So there's really no way around it. And then if we know it's replaced by something, then the naturalness problem, which we'll come to, is why is the scale of that replacement, the scale of that new physics, not reflected in the electroweak scale? How can we have a scale separation, which is a big one? Any other reasons we need new paradigms? Yep. Pardon? Yeah. So the point was you might need a new paradigm so that you can do calculations more efficiently. That's certainly true. We might get an understanding of QCD, for instance, which is very different from the old-fashioned sort of write down a Lagrangian, calculate scattering amplitudes using Feynman diagrams and so on. We might have a new paradigm in that respect. There are others. I think. Yeah, baryogenesis. We need some new physics to explain that. Baryogenesis doesn't work in the standard model on its own. This is a great puzzle to me. Nature gave us 3 generations. The only reason I can understand that nature would do that to us is to allow for CP violation, but then it didn't even use the CP violation. Caitlin, yes? Chiral fermions like. Yeah, yeah. So the comment was, nature has chiral fermions, apparently. We don't know how to put chiral fermions on the lattice, which you may have heard about in TASI. And in some sense, lattice is one of the best ways of defining a quantum field theory, where you understand how to do RG and things like this. There are others. So for instance, flavor. It's impossible, in my view, to look at the structure of Yukawas, the structure of the CKM, and not just but the up type quarks, the down type quarks, and the leptons. It's impossible to look at that and not see a pattern, right? There's clearly a pattern going on there. And for me, it's very reminiscent of the periodic table, right? There were clear patterns that were spotted by many people, Mendeleev, I guess, being the most famous, in the masses and properties of various elements. And so they could be categorized. And so we saw that there's a hint for an organizing principle. Where did that organizing principle come from? It turns out we needed to understand not only quantum mechanics. If you really want to explain that thing, you also need to be able to explain the structure of nuclei, which means you'll be able to explain why neutrons and protons exist, why they in certain ways, the nature of the strong force, the fact that ultimately this thing terminates because the Coulomb repulsion overcomes the strong binding force, and so on. And so you actually needed QCD and QED to really understand the patterns, the structures in the periodic table. And maybe it's the same for flavor, right? We see patterns, we see an organizing principle in the Yukawas, and we need the full ultimate description. Of course, we may be in my view, we may be a long way from finding that new paradigm. You know, imagine going to Mendeleev and saying, actually, you know, you're puzzling about this whole structure, but you're not going to believe us. But there's quarks, there's leptons, it's all based on a non-abelian gauge group. The QED bit that you were sort of anticipating is a minor perturbation on the structure of the light nuclei and so on. And so we may be a long way off. But anyway, so we need new paradigms. I'm going to focus on one in these lectures, which is the naturalness question and the paradigm that we need there, because it's going to enable me to show you the biggest range of cool stuff, basically. I'm using these lectures as a vehicle to show you some interesting QFT and non-QFT intersection with Cosmo ideas. And I want to do that, and this is the quickest way I can do it. I think this is a very important problem. Don't get me wrong, but there are also other important problems with very interesting potential new paradigms behind them. Okay, so what is the naturalness question? The naturalness question, in a nutshell, is why is the electroweak scale, or let's say the Higgs mass, much, much lower than the apparent cutoff of the standard model? Why do I say that? I say it because we haven't seen anything in the vicinity of the Higgs mass, right? We've done scattering experiments up to a PeV in some cases, even more than that in other cases, and we haven't seen anything. And so it looks like the paradigm that replaces the standard model is actually has states, naively it looks like this, that are higher mass than the electroweak scale. But as I said, when we look at the patterns of coefficients in an effective field theory, we normally call them Wilson coefficients. They're normally only unexpectedly small if there's some symmetry that we haven't spotted, or if there's some fine-tuning of parameters in the fundamental theory. And so this is suggesting that maybe one of those two things is going on. And that's going to be the subject of these lectures. I'm going to try and give you examples of where there might be symmetries. There's not a symmetry in the standard model that can do this. They can explain this question, but there might be symmetries beyond the standard model with their associated particles that come along with those symmetries that can explain this, or mechanisms that have actually fine-tuned the fundamental parameters of whatever replaces the standard model to make this happen. I'm going to give a couple of examples of how this might happen. In terms of fine-tuning of fundamental parameters, this is not something that we are totally unfamiliar with. So for instance, consider who has heard of a transition edge sensor? Obviously. Obviously, okay, no one else. So in a transition edge sensor, you get a superconductor, and you effectively, this is obviously going to be very oversimplified, but you effectively fine-tune the temperature such that it's sitting right on the superconducting phase transition. Essentially, this is a point where, in particle physics jargon, this happens. There's a state which is much lighter mass than you would expect, such that if there's a small perturbation in the temperature, by a small amount here, this leads, because this is very steep here, the resistivity, leads to a huge change in the resistance in that superconductor. So we do fine-tuning in the lab. Here, it's often done by some circuit that uses feedback to always push the sensor back to this point. Okay. So if that had happened here, we need some sort of circuit in fundamental physics that is fine-tuning parameters to be back such that you would be analogous to this situation. I'm going to give you, in not the next lecture, but in 2 lectures' time, an example of that. There's another place we see fine-tuning showing up. People often use the moon, but I'm going to use something timely, which is thorium-229. Who's heard of thorium-229? You had better have. Okay. You've heard of thorium-229? Is it used for CP violation?
You could use it for CP violation, but not yet.
Yeah, right.
Sorry, sodium oxide is used for
Okay, so yes then. Thanks for saving my bacon there. So, so thorium-229 is very interesting because it has a nucleus which has an excited energy state. I'm gonna describe this as the same nucleus that's sort of been excited, so I'm gonna make it a bit fuzzy. Which is something like 8 or 9 electron. I think I've written 8.3 electron volts. The excitation energy. What do we usually expect nuclear excitation energies to be? There's a large range here, but at least like a keV or something like that, right? So why is this excitation so small, such small energy? It's essentially fine-tuning. There's an accident that has happened, which is that lots of different contributions, or this is what we think at the minute, lots of different contributions. By the way, correct me if I say anything daft here. Lots of different contributions that are of the order of keVs, MEVs, and so on, and they've all cancelled against each other to give an excitation energy which is very, very small in nuclear physics terms. How can we understand that this has happened? Like, should you be shocked and worried about this fact that nature has fine-tuned thorium-229? Yep.
Maybe not, because there's a lot of transitions that could have been that small.
Bingo. Bingo. Yes, exactly. No, I'm not worried about it because there's a lot of nuclei, right? So, unlikely things happen in the context of many things, right? And so there's a lot of nuclei, and it's not surprising that this is 2 or 3 orders of that there's one of them where some accidental fine-tuning happens because there's simply a lot of nuclei. And so it could be that fine-tuning could come about essentially through some notion of plenitude. If you have lots of things and they're all sort of generic, then occasionally if you have so many of them, then rare things can happen. If you do lots of experiments, you can see, say something only happens 1 in 1,000 times. If you do one experiment and see it happen, you'd be pretty worried about what's going on. If you've done 1,000 experiments and you see it happen once, then that's no surprise. And it could be that this is behind this question here, and I will also give an example of that. So,
But if I could just add,
yeah.
so there is still a little bit of fine-tuning here because the next lowest first excited state in any nuclear isotope is 70 electron volts.
Yes.
So maybe you would have expected the next highest one to be 60, maybe order one number higher, but it's not.
Yes.
There's still a sense in which this transition is anomalously low. By accident.
Yes. So the comment is that there is a sense in which this is actually a little bit concerning because it's too fine-tuned, essentially, considering the number of transitions that we see. The next transition, excited energy state we see for a nucleus is around, did you say 70 electron volts? Right. And so if you had some distribution, you've got all of these nuclei, and they're all various different contributions, their excitation energies. You would expect some relatively smooth distribution, but this seems to be an outlier by an order of magnitude or so. Maybe that also will map actually into one of the questions that I will discuss. Okay, so I'm going to discuss essentially three options: symmetry as an explanation for a hierarchy between the UV, between the scale of the UV completion of the standard model and the electroweak scale, or fine-tuning, and within fine-tuning there'll be feedback mechanisms or plenitude as an example. I'm going to say all of the examples I will give you, I view as a quasi-paradigm, potentially, because none of them is fully satisfying in some sense. And so all I view as a potential work in progress. Okay, so we have 10 minutes left, so I'm going to actually move on to the next topic. But are there any questions at this point? We're now going to get into technical stuff and less of the blah, blah, blah. And so if there's any questions as broad as you wish, I'd be very happy to take them. Or comments? Nope. Okay. So now we're going to go into the first set of possible solutions, explanations, I would say, which is, yes?
Talk about differences, if any, between when people talk about naturalness in this context versus hierarchy. Are they just synonyms, or do they mean slightly different?
Okay, this is really, thank you, because you've just, yes. So the question is, I'm going to paraphrase slightly, are terms like the hierarchy problem and naturalness and fine-tuning synonyms, right? Are they essentially, when I say use this jargon, am I really talking about the same thing? And the answer is yes. So we'll see, you will see fine-tuning, naturalness, the hierarchy problem, the hierarchy puzzle, interchangeably being used for the same sort of thing. It will show up for sure in the context of what we call electroweak naturalness. By electroweak scale, where you can use that interchangeably with the Higgs mass, but also questions as well, like the strong CP problem, which we will actually discuss relatively briefly. Even in terms, there are different types of naturalness where one can understand why a parameter is actually, no, I'm not going to get into that. So yes, they're all, consider them synonyms. Okay, so the first set of potential explanations falls under the banner of symmetry. Using symmetry to explain this puzzle. By the way, I should say, I view BSM model building, which is essentially asking questions like this and trying to figure out what the fundamental theory is, as a very modest exercise. Sometimes it seems very immodest, because it seems like you're creating a theory, right? I'm deciding these symmetries, this person's deciding those other symmetries, and then we write everything down, we study the phenomenology and so on. That gives the wrong impression. Theorists aren't trying to play some sort of godlike creature that's deciding what nature is. We're guessing at theories, we're building these theories to try and understand what might actually be happening in nature, but in a very modest sense, they're guesses, and we know that they're guesses, and they're might be slightly wrong, but on the right track, or they might be completely going down the wrong track. So when I'm constructing theories, please do keep in mind that in the enterprise of model building, that people construct models because they're trying to take a punt at guessing what, looking at these clues and guessing what might be going on. They're not trying to decide what nature should be. There's sometimes a bit of confusion about that. Okay, so the first set of solutions asks the question, could the Higgs be pion-like? What do I mean by this? So, as you know, in QCD, you can consider it to be the UV completion of the chiral Lagrangian. The chiral Lagrangian is the theory, essentially, that describes pions and rho mesons and so on. So the UV completion has things like quarks that's coupled to gluons and so on. But then as we go from the UV down to the IR, you have things like pions baryons like neutrons, protons. We have things like rho mesons and so on. And this question asks, could it be the same for the Higgs? So that in the UV, you have something that might be like this, might be some strongly coupled gauge theory, but it might not as well. It might be something very different, which nonetheless, as you go to low energies in the IR, spits out as its lowest energy state the Higgs on its own. After all, there's a big mass gap between the mass of the pions and the mass of the rho meson, for instance. And keep in mind that these quantities should be, the metric for these quantities thinks of them in terms of mass squared. The parameter in the Lagrangian is the mass squared. So if you think about the pion mass squared relative to the rho meson mass squared, that's a big scale separation. And so this broad question, could the Higgs be pion-like, asks, could it be that the UV spits out essentially only the Higgs and no associated particles for a large energy range, which would then explain why we haven't seen things at the LHC? And could the mechanism for that be the same as the mechanism that made the pions light here? Okay, and that mechanism comes under the banner of spontaneous symmetry breaking. In this case, it's spontaneous global symmetry breaking. And we would describe the pion as a PNGB. Is this jargon that, who hasn't heard this jargon before? PNGB. Plenty, okay. So PNGB stands for pseudo Nambu Goldstone boson. Who hasn't heard of Goldstone boson? Okay, so I think the concepts are probably quite clear to you. Goldstone boson is essentially or a Nambu Goldstone boson is the scalar particle you get when you spontaneously break an exact global symmetry. And pseudo is when that global symmetry is broken by a small amount. So it's not an exact global symmetry, but when the scale of exact global symmetry, spontaneous breaking is much higher than the scale of no, that's not a very good way of putting it. Yeah, okay, I'll put it that way. The scale of exact global symmetry, spontaneous breaking, is much higher than the scale of explicit global symmetry breaking. Then you get particles whose mass are suppressed by the ratio of those two scales, so they're light. Just before we wrap up, what those two scales in the theory of pions, the scale of exact, I'm saying exact, but it's an approximate symmetry everywhere. The scale associated to the spontaneous symmetry breaking is what, broadly speaking? Pardon? No, that's a good guess. It's the QCD scale, essentially. That's the scale at which the quarks condense and spontaneously break SU2 axial, essentially, which is a global symmetry of the quark mass terms, of the quark kinetic terms. And what's the scale, and I just gave the game away, and what's the scale of explicit global symmetry breaking in this instance? We're going to go through all this again tomorrow, so don't worry. Pardon? Yes, the quark masses. So essentially, you expect the masses of the PNGBs to be proportional to, let's say, m pi squared, to be proportional to some mass scale squared in the UV. This would be lambda QCD. Suppressed by m quark over lambda QCD. This is very broadly speaking, of course. Where this is a small parameter. These are like 4 or 5 MeV. You can think of this as being in the ballpark of a GeV, and you would get the right answer. Why does it have to scale in this way? Because there's no reason it should scale as m quark squared. In the fundamental Lagrangian, right, you see that you just have m quark in front of the fermion, the fermion bilinear. But they should certainly become massless as we set m quark to 0, because then we recover an exact global symmetry. And so in here, you have a small parameter, which must scale in this way, multiplying the typical UV cutoff here. So this is all scaling just as you would expect by the rules of effective field theory. And the question behind the theories I'll discuss tomorrow is, could the Higgs be light for a very similar reason, almost the same reason, essentially. In terms of structural questions, really the same reason. Could the Higgs be like a pion? Could it be a PNGB? Okay, and I guess I should wrap up there because it's 5. But do you have any questions at this point about anything that I've discussed? Nope. I guess we leave it there then. Thanks.